Thanks for attending our DEHN Protects webinar series. I'd like to do a little bit of housekeeping and just remind people that if you've missed our previous sessions, you can certainly go to the chat section of our webinar and you can go find the link for our previous session. And I'd like to introduce myself. I'm Mark Hendricks with DEHN, and I'd like to introduce my colleague Stephen Weber, who is our webinar manager and organizer and all around effective man in the field.
Thank you, Mark. Welcome, everybody.
Yep. Thanks, everybody. So this is a quick overview of the sessions that we're offering. Today's session's Pillars of Lightning Protection. Next week, we're planning to do the Bond That Metal Stuff, which is an important aspect of protection. In addition, we've got a session later in the month to talk about expert applications. So welcome to the session. It's a rainy day here in Florida, and I'm expecting some lightning activity, so it could be an extra exciting episode today. So today's session wanted to cover some of the topics that have been coming up. We wanted to cover an introduction to the standards, just a brief overview to compare the IEC 62305 and the NFPA methods. Wanted to do a quick nod to father of lightning protection, Franklin rod system. The topics we're covering today basically were derived by Ben Franklin, published in 1753 in the Poor Richard's Almanac. And at the time, he even suggested using rod iron used by nailers because it was readily available material. That's what you went to the blacksmith, you could get these types of materials and protect your structures. So we're covering the basics, the air terminals, the down conductors, and the earthing systems. And remember, earthing is also for AC power safety and static discharge control, in addition to lightning protection. So we'll be covering the aspects of earthing that are most related to our lightning protection as it stands as a lightning protection system. And off to the side here, I've got a couple of sketches from some of Ben Franklin's original work and a slightly used lightning rod from that period that you can see as I would consider that we have better materials than was available than used by blacksmiths and rod iron. So we want to introduce the aspects of some of the I would say the more prevalent lightning protection standards, the IEC 62305 methods, and of course the NFPA 780 methods, which are prevalent here in the United States. One of the things I like to point out is that IEC methods are not that different from NFPA. And I use the words only better because I think it's more thorough and it gives you a more rigorous approach. But there's a few key issues that you find. The NFPA indicates that each building must stand alone, whereas IEC also allows consideration of adjacent structures if that's part of the surroundings. And what that really means is that if you've got a structure that's really tall next to you, you can benefit from the lightning protection offered by that taller structure. So in this illustration, you see there's a small battery plant that's below and adjacent to these other taller structures. And you can see that you get the benefit of coverage from a rolling sphere calculation of that structure relative to its surroundings. And that's one of the things that really stands out about the IEC methods. There's also a couple of really good questions that came in last week's session that talks about the comparison between separation distance and bonding distance. And the standards make it sound different, but really what you have is NFPA dictates that metal objects that are close to the down conductor and LPS system have to be bonded. And IEC considers it the other way around. It says things that are separate do not have to be bonded. It's the same thing. It works out algebraically. You can actually show the definitions of separation distance and bonding distance from NFPA are actually very similar. And it works out to be the exact same figures, very, very nearly the exact same figures for an LPL3 from NFPA, to compare NFPA to an IEC LPL3. So this is an important aspect. So just wanted to make sure that that's something that it's presented to the team, that you really can draw very close similarities between the systems. So the design approach from NFPA is basically, it recognizes that there's objects less than 75 feet, and there's a class that's considered class 1, and there are materials that are less expensive, less robust, smaller diameters, shorter tips, and the larger structures greater than 75 feet have larger diameter conductors, taller tips, and of course, that's a very brief description of it. There's it's a 111-page standard with a lot of details about how to implement the systems. But the real key is that it does recognize what's considered a 150-foot radius, which is essentially an LPL3 design. NFPA does also recognize that structures with flammable liquids would benefit from a smaller, a shorter rolling sphere radius, and that's an important aspect of the NFPA standards. The philosophy of IEC is really to start at risk, discover what's important about your system, and then apply the LPL level that you need for that level of risk. So it gives you a lot more flexibility to select methods, materials, spacing that will benefit your system. It gives you a lot more ability to tailor the lightning protection system for your application. The risk analysis from IEC has a very detailed approach. There's some really great software tools available. The risk analysis from NFPA is consistent of Annex L, and it's actually considered an optional exercise for most applications. And it's a little bit cumbersome because there's not a lot of great software tools available. I know that there are Excel spreadsheets out there that might be very effective for this, but it's a little bit cumbersome methods. And it's not required as part of your approach to your LPS design system. And this slide I really like to show because it describes in pretty much one slide. You can see the rolling sphere radius, you can see your different protection angle methods, you can see the differences between the lightning protection systems, the LPL levels from 1 to 4, where LPS level 1 is the most stringent. It's a small radius to show that lightning might get into the nooks and crannies, and it gives you the ability to use less stringent methods as your risk may allow. Another key difference is in the inspection of your lightning protection system. The IEC methods give you a really great suggested methods. It walks through your entire project from front to back, end to end, and it gives you the ability to draw right from the standard the inspection and maintenance protocols that you might want to employ for your lightning protection system. And I love this picture of a frayed pigtail bonding into the lightning protection downcomer, because it shows you what you really need to watch for, because this is going to be a real problem. And of course, all the way through final master label certification as needed for your applications. Another really key difference between the standards is that the IEC materials are required to be tested for the purpose with injected lightning currents. Most of the NFPA materials are established by review of the the mechanical parameters, the mass per foot of the down conductor, the diameters of the tips, the diameters of the earthing rods. And we can see that in IEC methods, these materials all have to be actually tested for the purpose. And this is a real key issue. There's also certain tests that the NFPA and the UL standards don't even recognize that are relevant for direct strike lightning protection applications. So this is another key aspect. You know, it's really important to point out that NFPA methods protect a lot of lives, and it's a very effective system. So by all means, it's a valid and very important set of standards that is for fire protection. The IEC methods, we feel, give you more rigorous approach. So that is a very brief comparison of the two standards. There's a lot more information available in public domain. We've written some white papers. There's forthcoming changes to the standards, and we feel that there's a lot of information. That topic alone could go on for at least a debate of several hours between experts. So don't want to stir the mud too much, but I want to make sure that some of the key points are discussed. So the pillars of lightning protection. What we're going to talk about today are the first three pillars. But one of the things I want to remind you is that in all these aspects, you can't ignore one or the other in favor of, say, your down conductor system. You always have to pay attention to the other aspects so that it's a coordinated approach. It's not a menu. You don't just get to pick the first three and ignore separation distance. And that's what shows up in a photograph like this, where if you ignore separation distance, it's at your own peril. So this is a nice illustration, a nice photograph showing what can happen when you're not paying attention to all five pillars. Today, we're going to talk mostly about the first three, but I always want to make sure that the audience is aware that you always want to pay attention to the full aspects. Air termination system, the air terminal system. So Ben Franklin figured it out. You put up an air terminal, and it serves as a preferred attachment point for the step leader, that last striking distance where the lightning charge builds up over an area, and all of the objects, we saw that in some photographs last week, all of the objects send up little tendrils trying to reach out to that lightning charge, and one of them will attach. So what we're showing by having air terminals is the calculated equivalent electric field. So you can see in something that looks like a rolling sphere calculation that the air terminal gives you the equivalent electric field over that building. And what the purpose of the LPS system is to give that lightning charge an air terminal to attach to. And what you see in an illustration like this is that all of this equipment, these chillers and condensers on the top of a building, maybe it's a radio, maybe it's something else associated with a very sensitive asset. Well, those objects on the top of that structure can be protected from the lightning direct strike because the electric field sees the air terminal first, and it has a stronger effect to the electric field. And so that's what the rolling sphere calculation shows you is the equivalent electric field approximation. And what's nice about a sketch like this is you can see that you can use taller masts to extend that reach. You've got shorter masts maybe along the parapet of the building that might look like what you'd see in an NFPA system, but you can also use taller masts associated with extending that rolling sphere coverage. These are a few slides that really help describe, what you're basically building is an air terminal down conductor earthing system. And the mounting dimensions are very similar between NFPA and IEC. In IEC, we're talking about holding the conductors a maximum of 1 meter apart. NFPA says 3 feet. Pretty similar. Again, the standards are not fundamentally different. They're actually fundamentally similar. And there's only things that I would say give IEC an advantage and gives the designers some ability to really fine-tune their system. You can see that the methods would appear virtually similar between IEC and NFPA methods. You can have an array of small terminals around the edge of a parapet, and then you'll have down conductors spaced at intervals that are appropriate for the lightning protection system connection into the earthing. So again, I like to say there's more things similar between them than are different between these two types of standards. So what's important about an image like this is that you can use the structure as a natural down conductor, but you really have to pay attention to the material thicknesses, the material types. You can use it as a natural air terminal, but notice in this photograph, it was struck by lightning and it's got a 2 or 3 centimeter hole that was impinged into this metal flashing. And for something like a building, maybe a residential, that could start a fire. If this was something that was holding flammable liquids, you would have had a very serious problem with a structure like this. And so the standards give you a lot of guidance into what you can use, what the materials are, and how thick and how robust the materials have to be in order to serve as a natural down conductor. NFPA has very similar tables as to this, where you're showing the types of materials and the minimum thickness. There's also indications in the standards that allow something like a big thick metal oil tank to serve as its own natural protection, as long as it's earthed correctly. So the standard allows you to use your discretion and to evaluate the materials of the structures and determine what you can use and what you can't use as natural components to avoid that direct strike and that direct damage. So an image like this, a photograph like this, is really nice because it shows you can have your air terminal, but you want to make sure it's properly bonded to the metal materials around it. This goes back to that discussion of separation distance and/or bonding distance, where if this down conductor terminal is too close, you have to bond it. If it's separated far enough, you do not have to bond it. But in this case, what we're showing is that all of that, the air termination system and the bonding methods between it, all have to be very robustly bonded. And that's why I like that term, bond that stuff, that my colleague Stephen came up with. So now we'll talk a little bit more about the down conductor systems. The down conductor serves to bring that lightning current to Earth. And that's where a lot of the problems with separation show up, that if you're next to this water pipe, you don't just get to run it parallel to it because it'll flash between that water pipe. In the IEC methods, we also want to talk a lot about how you connect to your earthing system and how you test and inspect. That was a real key aspect in the standard that we talked about earlier, that the IEC methods really want you to focus on test and maintenance. As much as we want to install a system and turn around and walk away from it, the lightning protection system is there for fire protection. And so you don't want to ignore it. So every year, for instance, your fire extinguishers your fire extinguishers are inspected. Why wouldn't you put the same emphasis on something else that's going to save your life in your building? So there's a lot of emphasis on these types of connections. But we really want to talk about that down conductor system. So it's shall be installed straight and vertical. You're trying not to do loops. You're trying not to do big S curves. You're trying not to go back up the side of a building. It's really important to understand that lightning wants to get to Earth. And if you have curves and all sorts of weird configurations, it's probably going to cause side flash in itself. If you had a big curve or a big S curve in this down conductor, it'll impose more inductance. So when the current is flowing through an inductor, it will build up more voltage and it could build up to side flash. So that's one of the key aspects. You want to make sure that the position so that separation distance is not ignored. and you want to make sure that you are properly using natural materials correctly. So if you're going to use your rain pipe as a down conductor, which is tempting because it's part of the natural structure of the building, you want to make sure it meets the requirements of the thickness of those materials so that you're not punching through that metal and then causing a problem all of itself. Connections, of course, can be clamped, crimped, seaming, screwing, bolting, and of course, exothermic welding, brazing, things that are high temperature operations. You're not just going to use a little bit of electric solder to put together a lightning down conductor, because that will, of course, fail when you need it most. And really the point is that you want to make sure that your down conductor system is clean, effective, the spacing obeys the standard, and that you have proper connections into your earthing system. The point about this slide is that we really want to point out that you want to be able to inspect both the connections to the earthing system and then the earthing system itself. You'll have things like test joints and test boxes where you can go back and look at your individual test connection. What's nice about this illustration here is that when you come out to this particular site, you can test this connection with something like a clamp-on meter that will show you that it's connected both upwards into a loop above ground and then downwards into a loop below ground. And then with having a test joint, you can pull that apart and isolate it, and you can find out if you have, for instance, a severed earthing cable buried below ground. So by having a test joint, you can isolate those connections and actually effectively troubleshoot your earthing system by looking at your test through the test joints and isolating and then reconnecting to help you find where there might be problems with your bird system. Again, the standard has a lot of information about the spacing, what you have to keep insulated from each other, what the spacing between connections are, what the spacing between the down conductor should look like, and then how your connections into the earth must appear. So there's a lot to be said about just down conductors. Again, each of these topics is something that we can talk about individually for its own 1 hour segment. So I want to remind everybody this was a summary, and we don't want to go overboard with individual topics. The down conductor system separation distance. This is back to that discussion we've had before, where you need to pay attention to your down conductor system, but you can't ignore the other aspects of the pillars of lightning protection. You don't want to introduce side flash into other important systems that would go back. For instance, here you've got a sensor that will go back into your main building, and you can destroy your valuable controller systems accidentally by introducing side flash. And the earth termination system. This topic is really detail oriented. There's a lot of information on this, and I want to point out that some of my colleagues probably have forgotten more about earthing that I even know about. So the point here is we're going to summarize the type A and type B systems from the IEC standards, which by the way are very similar to what you find in NFPA. So this slide basically points out that your type A system can consist of an individual connection into the soil. It can be vertical as an earthing rod, or it can be horizontal. And remember, this is a very boots in the dirt sort of conversation. When you're out trying to install an earthing rod and you hit bedrock, you can't sink a 9 meter or a 2.5 or a 4 meter earthing rod into bedrock. So now you're faced with achieving the same electrical contact to the soil by going out with horizontal radials. And that's an important aspect. And we'll see some more information on this. In a type B system, we're really looking at what looks like a ring around the system, and it can also include buried earthing vertical rods. which is equivalent to what might appear as what's called the foundation earth electrode. And we'll talk a little bit more about that too, because in many places, for instance, in urban areas, you're not going to get to run horizontal radials into your neighbor's yard. You're not going to get to run vertical earth rods deep down into concrete or into the electric utilities or the gas line utilities. So you have to be very careful in many applications. And NFPA and IEC both recognize that a foundation earth electrode will serve as a suitable lightning protection earth electrode if done properly. In the NFPA methods, they describe that if you properly test around this perimeter, you can show that the impedance is suitable to serve as a lightning protection earth electrode. And so these are the basic illustrations of what it should look like. This is a really nice slide. We talked a little bit about it last week, but what's really great on this slide is that it shows you the options that you have with the IEC methods. If you've got a very important asset, and I like to use the word hospital full of babies and explosive oxygen, you want to impose stricter lightning protection methods. And that's what the IEC methods can dictate here. So in a chart like this, what you can see is that in a class 3 type system, the depth of the earth electrode is about, the maximum, it's about 5 meters. That's the connection that you want into the soil. And it's pretty much regardless of the soil resistivity. You'll get suitable connection to the soil. But as you go into the more stringent lightning protection class, what you see is when you get into these high soil resistivities above, say, 700 ohms centimeters, it allows you to then evaluate and install a deeper and or longer earth electrode system to get you to the same equivalent connection to the soil. And what's nice about this is that the risk analysis tells you which class to use, and then a chart like this can tell you how deep that earth electrode is depending on the soil conditions. And so this is a discussion that goes back to having your boots in the dirt. You actually need to understand what the real site conditions are. What's buried under the earth and what is that earth soil resistivity. And that's what's really great about a slide like this. It really gives you, in one slide, you get a lot of guidance into what it's going to take to create a suitable earth electrode system. And so here's an illustration of that horizontal earth electrode from a type A system. It is allowed to have an earth rod unto itself. In other words, this rod does not have to be connected to every single other earth rod around it. It's allowed to be sort of a standalone rod. And in this case, we're seeing it as a horizontal radial. Of course, it has to be buried below the frost line, and it needs to be at least the distance as indicated by the previous slide. Remember, it had to be at least 5 meters of contact with the soil. That's what the standard's telling you to do. And if you need more, you run more horizontal length and more horizontal radial electrodes. And that helps you build up to meet your customer's requirements. Here in the USA, the Article 250 for your AC power earth electrode is 25 ohms. So that can be achieved by going back to that calculator, running that earth electrode the distance required to get 25 ohms. We have customers that mandate that they want a 1 ohm connectivity to the soil. You'll see things from other customers where they'll talk about 5 ohms. So you can use your requirements, and then you can get to a properly designed earthing system that connects to the air termination and the down conductor system. And that spacing is all spelled out by the standard. So we'll see a little bit more on that. Vertical rod, very similar. You have the standard tells you how deep the rod should go. Basically at least 2.5 meters, but 9 meters recommended, which is a very deep earth electrode, by the way. And of course, you need to stay away from the side of the building, approximately 1 meter. And you'll see this very similar types of aspects where it's buried below the frost line. The actual connection that you're making needs to be buried below the frost line. This can be clamps, exothermic welds. I'd like to show this test joint as a clamp connection. If you make an exothermic weld with no test joint, that meets the intent of the standard, except when you come back to test, you don't have a separable connection. You can't troubleshoot that system without severing that exothermic weld, which is difficult and expensive to do. Of course, there's some important aspects about the electrode, how deep it must be buried. It shall minimize effects of corrosion, freezing, frost line, that we talked about that a little bit. And it should be evaluated for the length to meet that table that we just had looked at. Of course, 9 meters have been proven to be advantage. There's great advantage, but that's you can see that in many soil conditions, that's going to be very difficult to achieve. So here's a few illustrations showing what that looks like in practice. And you can, even this one photograph, you can sit down and we could talk about this for quite a bit of time. Right here, there's a buried cable next to it. Is there proper separation distance? You can see that you're looking at what looks like stones and some concrete around it. So you have to take in the actual surroundings into your design to account for what's actually in the system. Clamps and exothermic welds work in a similar manner. Clamps in particular need to be protected. If you're using a clamp method, it's required that you protect against corrosion effects. And so, of course, the use of steel and inert materials will go a long way to achieve those results. We just want to point out that there's lots of methods. Type B earthing arrangement, and this is the ring or foundation earth electrode. This is also very similar to what you see at large facilities where they have a buried mesh around the whole plant. We do a lot of work with customers that have multiply connected buildings, and so you'll see what looks like multiple ring arrangements that are all interconnected. There's some combination of the ring, vertical earth rods, and what's nice about a slide like this is that it tells you that it is recommended not less than the number of down conductors with a minimum of 2. So every down conductor is intended to have a connection to that earth electrode with at least 2 down conductors and 2 earthing connections. And remember, if you can't do it vertically, you can go horizontal or inclined. The standards allow for you to adapt to the soil and the local conditions. So an important aspect of such a ring electrode is connecting to it, because you're not likely to have a easy to achieve connection into your foundation. And so what is important is to have these types of exposed connections that you can reach when you go to install your down conductor system. So what's important here in this particular slide is we're showing the approximate appearance of what that ring would look like. But what we want to make sure that we call out are these connections that you can now get to and actually make your connections into that earth electrode. There's a lot of guidance in the standard, what that should look like, the types of materials. You want to be inert, you don't want to have rusting, and you want to avoid things like dissimilar metals that will cause accelerated corrosion. So again, using the guidance of the standard will get you a long way. One of my favorite quotes is from my colleagues, "Hey, what should I do with my earthing electrode?" And the answer is, what does the standard say? So in one slide, it's very difficult to give you all the information, but the standard does give you a lot of guidance. So If you're using your earth electrode as part of your LPS, there's requirements that those connections be not more than 10 meters apart. So what's nice about a slide here is you see some important aspects, the recommendations for the terminal lugs, where you can get at it, the interconnected bonding of that system. You've got equipotential bonding conductors that run with the rebar. And so in one illustration like this, you see a lot of your key aspects of actually building a functional earth electrode system. I've got a couple of nice illustrations and photographs showing the actual rebar steel connected to the down conductor systems. And what's nice here is that in this photograph, you can see this is really common. If you've done a lot of concrete work, you'll see these straps that hold the rebar in position, but that is not an electrical connection. So if you're only using these wire straps, you miss the whole point about having a bonded, interconnected earth electrode. So if all you had were these wire straps and you had lightning induced into this concrete, you would see a lot of sparking buried in the concrete, which will inevitably cause the concrete to stall and fail. So one of the points I like to make when I talk to young people that are entering the industry is that you may know everything there is about concrete, but don't ignore bonding all that inner space steel. And so what might be manifesting as failure in steel in the concrete could actually be lightning induced damages, that your interconnected steel, these rebar members, are not actually bonded suitably for the purpose of controlling lightning currents. So this photograph, you can see this is a big mesh of what looks like the rebar in what's going to become the floor of a building, and you can see some vertical struts of the rebar rising up out of the concrete that'll connect to what might be pillars. And in this type of photograph alone, you could see that where all your problems are going to be. You're going to want to go back. You're going to want to make sure that the rebar is suitably interconnected to form a suitable earth electrode. So I've got a series of illustrations that sort of walk through what this should look like when you're doing an earth electrode system. So you have your buried dirt and you're ready to start preparing, and you want to prepare this ring with your vertical risers. See these red vertical risers become connections to the rest of the building steel. And this is what that might look like in practice, where you've got the initial 10-meter grid, 10 by 10 meter grid, because for the intent of using this as an LPS system, you need to have a 10 by 10 meter grid. So you've got your vertical risers coming up so that you can connect, in the future, you'll be able to connect to your LPS. So then you put a blinding layer to reduce some of the touch step potential issues that you're going to see within your building. And then you start laying in your reinforcement rebar. And again, we talked about some of that, the detail, the devil in the details of making all those connections. You want to have reinforcement connections every 2 meters. If it's functioning as your your buried system, you need to be 10 meters apart. If it's functioning as another form of electrode, you need to make sure it's not greater than 20 meters apart. So this is what that next layer of preparation might look like. In a photograph, you can see now you've got your rebar interconnected with conductors that are for the purpose of conducting lightning currents. Rebar is not a particularly great conductor, so we want to make sure that we're controlling that voltage with conductors that are for that purpose. So then we start adding layers, and this is the connections that in the future, you can see you'll need that connection in order to bond to your down conductor system. There's again a lot of aspects about this type of an illustration that you can use to guide the contractor systems when they're installing the buried rebar. This is something that might be that a nice example of what that bushing should look like. That it has a watertight connection into the system, so you're not constantly bleeding water into your concrete. But the point is that you want to have a connection available for your earth connection to the down conductor. And then when the final concrete slab gets poured, it'll look something like this, where all that buried work is now invisible, and the result is that you have connections suitable to connect onto your down conductor system. We've got a few slides that talk about the actual materials that are suitable for the purpose. Again, you can go back to the tables, you can look at your materials that you're using, you can see what's been installed. It is possible to go back and look at a system and measure to see if it's been installed correctly for the purpose of serving as a down conductor LPS system electrode. So what's important here is that if you follow the standards, if you pay attention to the materials that you're using, you can achieve a functional earth electrode suitable for that purpose. So I just want to open the floor to questions. In our last session, we didn't have much time for questions, so I want to open that up to the audience if there's some questions. Stephen, do we have any comments or questions coming in?
Yes, Mark, we did receive some questions. The very first question that we received from Ali was regarding the separation distance calculation that you referred to. He's asking, is there, in other words, a minimum separation distance that we need to adhere to? Or, yeah, how would you respond to that?
Well, okay, well, it's actually dependent on the lightning protection level that you've selected. So the NFPA standard, I believe, is a little bit more relaxed because it talks about separation and bonding distance relative to the closest connection to the LPS system, which is a little bit misleading because that implies that the voltage only builds up relative to the next connection. The IEC methods talk about that it's relative to Earth. So using the same calculations can get you slightly different results, but it really does depend on the height above ground and the type of system you're installing. That's perhaps the short answer.
Great. And then we have a question here from Muhammad. He said, considering a class 4 lightning protection system, how do we decide that we need to put air termination rods every 20 meters or on the conductor crosses or just at the outer corners and the high points and objects? So how do we decide that we need to put air termination rods?
Well, Stephen, I might let you answer that one. How would you approach that?
Yeah. So Muhammad, we would follow one of the methods that are in the IEC, like the rolling sphere or the protective angle method. And, in using one of these methods, we can determine what is the protective zone that we receive from an air termination rod. And that then allows us to determine where we need to place these rods. Saying that we just have to put them every 20 meters, it is a recommendation in a standard that we do put them on the outer corners where we have charge concentration on the structure, and on the higher areas. I mean, putting them on the higher areas just allows us to really lift up that protective zone that we can receive from the air termination system. So it all comes back to you're using one of the methods, the rolling sphere or the protective angle, to determine where I need to place this rod to get the optimal protective zone over whatever I want to protect. Then Mark, we have a question. Ricardo would like to know what kind of parameters are considered to determine the horizontal earth at least 5 meter requirement as it is in the standard.
That's actually an interesting question. So is the question, where does the 5 meter minimum come from?
Yeah. So what kind of parameters are considered when we say that the earth electrode has to be at least 5 meters standard?
I actually don't know where that comes from. But it does link back to soil resistivity and the fact that you need to maintain suitable connection to the earth. 5 meters is a reasonable estimation of the length of that conductor. Keep in mind that you also need to keep those terminals apart a certain distance, otherwise they just fall within the influence of its neighbor. So it's a combination of the length of that radial and then keeping it away from the other radials that might be around it so that they remain effective. I actually don't know where the 5 meter figure comes from, but it's back to some of the assumptions that come into the standard in the first place, and it was agreed upon by industry experts.
Yes, I agree. And then
if there's some historical background to it, I actually would be very interested, because there's actually a lot of things in the standards that are like that are sort of, well, that's the number that everybody agreed on. Okay, use it. It's a reasonable engineering calculation.
Yes. There's a question here. What should your mesh size be for the foundation earth electrode system?
The mesh for the interconnection needs to be minimum of 10 meters if you're using the foundation earth electrode for your LPS system. So the interconnected mesh, when we say that interconnected mesh, that's the mesh of dedicated conductors that are for the purpose of lightning protection. So that's a 10-meter mesh. If you're not using the system as a lightning protection, part of your lightning protection, it can be a 20-meter mesh. Yes. And that builds a nice, clean, equipotential bonded system so that you reduce touch step. I believe that's the correct answer for your question.
Yes, and then we have a question here. What is the best earthing ohm value for a residential project, and the best earthing conductor or material to use for such a project?
Well, a residential system in the United States, National Electric Code, Article 250, indicates that your earth electrode for your AC power needs to be 25, not more than 25 ohms. And what we often see is that that electrode becomes part of the overall LPS system as well. And so if you went to the electrical standard, it would be 25 ohms, which seems excessively high. So a lot of the question comes back to, what is the impedance of an individual rod, and how do I build a system that has an equivalent electrical impedance into the soil? That exercise is actually a very detail-oriented exercise, where you'd have to get your soil resistivity, understand the conditions, and then start placing your earth electrodes relative to where your down conductors are going to be as well. So it's actually, there's a lot of simultaneous factors that all have to be solved and satisfied.
And a really nice question that we have here is, can the HVAC ducting as down conductors if the sheets mentioned comply to the IEC standard thickness?
HVAC is notorious for very poor interconnected bondings. Even if the material is thick and robust and meets the standard minimum thickness, what you see in HVAC is what look like folded and crimped joints that aren't actually very well electrically bonded together. So the other portion of HVAC is that it's inevitably going to lead back to some very valuable air handler, chiller system, and control system. So you're actually putting the lightning currents directly into the structure where you may not want to have the lightning currents diverted into. And then you have to pay attention to every single joint through that HVAC system. And by the time you put your walls and your drywall up and you've covered it all up, it's virtually impossible to go back and put in bonding joints that are suitable for the purpose.
Yes, we have a
That
question about.
it's a really good question, and it might
about
work if properly engineered.
Yes, no, I agree. And then we have another question here that I just want us to get to. It's regarding the separation distance, where he's asking that generally when we calculate the separation more than half a meter, 0.5 meter, it always gets more as we go higher from the earthing system. It's generally more than 0.5 meters from the wall. How can we put all down conductors at the separation distance from the wall? It's not feasible. Any rule of thumb is Mark, if I just have a comment to make here, that I just want him to understand that if we calculate the separation distance, we're not saying that the down conductor and lightning protection components need to be that distance away from everything structurally. We're saying that it has to be that distance away from any other metallic conductors or grounded metallic bodies, anywhere where lightning will flash over and be conducted into the structure to cause damage. So the separation distance calculation does not mean it can't be installed within that distance on a wall or anything. It just means that I don't want to have that flash over to any metallic grounded metal bodies. I don't know if you want to add something.
Yeah, if you're within that distance, the intent is to bond it. So that down conductor would come down the side of a building, and if the building has metal flashing, you want to bond it at the top and bottom. You see a lot of these prefabricated buildings with this. There's a brand name called Nucor, and it's a thin aluminum sheet with a foam, a foam core, and it's way too thin to serve as a natural down conductor. But if you don't bond it, it'll spark to it anyway. So when we bring a down conductor past those elements, the rain gutters, that type of thin walled construction material, we want to bond to it. So you could hold it away half a meter or bond it. So it's back to what's the building structure look like, and what are you capable of? What are you able to do? So if you can't keep it a meter away, you bond to it. And it's how do you know what's inside your wall is another big question. That's why you really want to make sure that everything's bonded. Okay? And that's where my good friend Stephen, that's that term, bond it. If when in doubt, bond it.
Yes, and a follow-up question I see here is also where Ali asked, does the exhaust fan or a vent on a roof need to be sorry, I lost your question. Need to be covered by an air terminal, or does it only need to be bonded? So this kind of leans towards what we've seen in NFPA installations. Your comments on that, Mark?
Yeah, it's back to that discussion. If you can't install an air terminal to get it above those sort of victims, then you need to bond them. And what we see in some NFPA systems is they're basically using that vent and installing a bonding conductor as a mesh, maybe a cross conductor, and then putting a tip on it. And that is okay, except that where's that vent going? What's it actually connected to? So yes, you would want to install a tip on it, but it might be better if you raise the coverage above that vent entirely and then let that metal do its thing and not actually be part of your LPS.
Yeah, it kind of comes back to the question about the vent of a HVAC system as well. I mean, if you bond these vents or these HVAC ducting together with your LPS components, you run the risk of injecting lightning current into the structure itself. So this is a risk that you need to determine. Is it acceptable for you to inject current that way? If not, you have to maintain that separation distance away from these vents and these HVAC ducting, and and make sure that lightning current stays separate away from it, and then provide air terminals that are higher than these vents to create a zone of protection over these vents rather than installing a terminal on these vents. Mark, we have a question from Ricardo. He's asking, how can you determine the impedance of a lightning protection system? Is there a formula to determine that?
The impedance of a lightning protection system, it's not necessarily a set formula that I've seen. Is what we do. Maybe I'll apply the measures that we do when we're installing our systems. We'll measure. We'll put a clamp-on meter right at the pigtail connection to the earth, and that allows us to essentially look at a resistive network upwards and downwards, and we're proving that there's a connection. To ask, is there a preferred value? You know, you can always say, well, less than an ohm is a target value, but it really matters that all the connections look approximately the same. And then when you see one that's an order of magnitude or more higher than its neighbor, you know there's a problem. So it's not necessarily that we've got a target value. It's that you want to use it as a measure of troubleshooting. And that we've seen to be very effective, because when somebody's got, maybe there's an earth ring and it's been dug up by a bulldozer, that type of problem shows right up, because that pigtail, that clamp-on measurement is substantially orders of magnitude different than its neighbor, and then you know there's something different. So the standard, I've never seen anything that looks like a target value to put a clamp-on meter and say, okay, I see 1 ohm. I've never seen necessarily something that looks like a target value like that. But when in practice, we see stuff that looks like tenths of an ohm.
Yes, I just want to mention that the only thing that the standard say is that if we do use the reinforcing or the reinforced steelwork within concrete columns and within the structure itself, we can do a impedance test that way, and the standard does say that that needs to be 0.2 ohms. But
now is that the 10 amp test?
Yes, exactly. Yes, that's with the injection of 10 amps. Yes.
Yeah, you inject 10 amps, and then it looks for what should be a low impedance if you're using the foundation. Yes.
Yeah.
If you're using that is a valid
concrete.
Yeah, but it only is looking at the earth electrode. It's not really looking at your whole system. And you need to run that test without other things installed. Otherwise, it'll obscure the actual effect of the earth electrode.
And while we're on this topic, I brought this topic up because we have a question here. Is it preferred, in other words, to have these down conductors inside of the concrete with the reinforcing and the rebars, or to be on the outside of the building with down conductor holders?
If you're going to use your natural structure, then the standard indicates that the down conductor should be buried within that concrete pillar. That's what we've seen. You can derive that from the standard. If you're not going to use the pillar, then you can have your down conductor mounted as the structure allows.
Yeah. I think it's a matter of when you get when you get started on the project. I mean, if you are involved with the project from the beginning, and aesthetic issue, I think it is actually preferred to just leave or get the down conductor within the concrete, bonded to the reinforcing as it heads all the way down to the ground. That also adds it also adds a bit of when we talk about the electromagnetic screening that we also can receive from reinforced steelwork. But obviously, if we get pulled into a project once everything is already standing, you have no choice but to run a down side of a structure.
Yeah, legacy structures.
Then can we use an oil tank body, a properly bonded and earthed oil tank body as the down conductor, or an HVI kind of conductor as shown on the DEHN literature?
Can you use an oil?
Yeah, so can you use, if we need to protect an oil tank or a water tank, can we use the actual steel of the tank as natural down conductor, or do we need to run some sort of an additional conductor down?
No, that's if it meets the thickness of the to the tables, and it usually comes out to, what's the number, 5 millimeters for most materials. If it meets the thickness, it can be considered a natural down conductor. And that's similar between NFPA and IEC methods.
Yes, yes.
But that also, for an oil tank application like that, then you have to pay a lot of attention to the earthing system, because now, you know, the tank sits on the ground. There might be a membrane to prevent it from leaking, and now you really got to pay attention to how well that tank is physically earthed into the system.
Yes, agreed. Unfortunately, we've run out of time, Mark, but we still have a few more questions. And like before these questions afterwards, we'd just like to say thank you to you, Mark. It's been a very nice presentation. And thank you, everybody, for joining us. We have our next session, which I will send some invitations directly to your emails. As a general point, this webinar is recorded, and we will be sharing the recording link to you guys directly as well. Yes, so if there's any further questions, you will have my emails, Mark's email as well. So just send us a direct email and get you.
And yeah, we'll be answering all the questions that did come in as well, and make sure that everybody's try to make sure that everybody's resolved. And thanks a lot, everybody. Appreciate your time. We'll see you soon. Be safe out there.
Thank you.